A dark wound stretches across the face of the sun. Right now, at this very moment, a sunspot complex wider than 130,000 kilometers dominates the solar surface. That is 10 times the diameter of Earth. A gaping chasm of magnetically tortured plasma, pointing directly at us like the barrel of a cosmic weapon. What makes this phenomenon so unsettling is not merely its staggering size. It is the eerie familiarity of its form. We have witnessed something almost identical before. In 1859, a sunspot of nearly the same proportions unleashed what scientists now call the Carrington Event, the most devastating solar storm in recorded human history. Telegraph lines erupted in flames. Operators received electric shocks that knocked them unconscious. The night sky over the Caribbean blazed red with auroras that had no earthly reason to be there, thousands of kilometers from the polar regions where such displays belong. Now, 166 years later, we are staring at its twin. But here is what keeps the world's leading solar physicists awake at night, monitoring their instruments with growing unease. In 1859, human civilization ran on steam engines and copper telegraph wire. Today, our entire existence floats on satellites orbiting overhead, pulses through fiber optic cables stretching beneath oceans, and breathes through power grids that span continents. A Carrington-class event striking Earth tomorrow would not simply inconvenience us for a few hours. It would systematically erase the infrastructure that makes modern life possible. The estimated economic damage exceeds $2 trillion. The blackouts could last not hours, not days, but potentially years as we scramble to replace custom-built transformers that cannot be manufactured quickly. And the sunspot complex that could trigger all of this chaos is active right now, hurling plasma into space, building magnetic energy with every passing hour, coiling tighter like a spring under impossible tension. By the time you finish this documentary, you will understand exactly what we are facing. You will comprehend why the next few weeks matter more than any other moment in the last decade of solar observation. And you will learn what the scientific community is too cautious or perhaps too frightened to say out loud. The sun does not sleep. We have been conditioned to think of our star as a constant, reliable presence, rising each morning with clockwork precision and setting each evening with equal predictability. But that comforting image is an illusion constructed by the limitations of human perception. The reality beneath that golden disk is far more violent, far more dynamic, far more terrifying than most people ever consider. Beneath the surface, we see lies a churning ocean of plasma, a massive sphere of hydrogen and helium undergoing constant nuclear fusion in its core. At the sun's center, temperatures exceed 15 million degrees Celsius, creating pressure so intense that hydrogen atoms are forced to fuse into helium, releasing the energy that makes all life on Earth possible. This energy gradually works its way outward through the radiative zone, then enters the convective zone where hot plasma rises to the surface, cools, and sinks back down in an endless cycle of circulation. On the visible surface, the photosphere, where temperatures drop to a comparatively cool 5,500 degrees Celsius, something strange and ominous emerges from time to time. Dark patches appear, regions cooler than their surroundings by about 1,500 degrees. These are sunspots, and despite being cooler, they are anything but calm. They form where intense magnetic field lines have become so concentrated, so impossibly tangled, that they actually inhibit the normal convective flow of heat from the solar interior. The result is a darker, cooler region on the sun's surface that can persist for days or weeks before fading away. But sunspots are not merely cosmetic blemishes on the face of our star. They are the birthplaces of chaos, the staging grounds for eruptions that can reach across 93 million miles of space to touch our fragile technological civilization. On November 28, 2025, something extraordinary began rotating into view on the sun's eastern limb. Astronomers monitoring their instruments noticed a dark region emerging from behind the solar horizon. As hours turned into days, it became increasingly clear that this was no ordinary sunspot. It kept coming and coming, an enormous structure that required more than 2 full days to rotate completely into Earth's line of sight. When the complex finally revealed itself in its entirety, the global scientific community fell into a kind of shocked silence. The active region, now designated AR4294 through AR4296, spans an area so vast that NOAA was forced to split it into 3 separate numbered regions. Their classification systems, developed over decades of solar observation, simply could not handle a structure of this magnitude. We are looking at 130,000 kilometers of magnetically tortured solar surface, multiple dark cores each the size of Earth, all writhing with barely contained energy. And at the heart of this monster lies a magnetic configuration so dangerously complex that scientists have given it the most ominous designation possible in their classification system: Beta Gamma Delta. Think about the implications of that designation for a moment. We have developed classification systems specifically designed to assess how likely a sunspot is to explode with catastrophic force. And this one has earned the highest threat level we can assign. Beta Gamma Delta means the magnetic field lines within this region are not merely complex or tangled. They are chaotically intertwined, twisted around each other like serpents locked in mortal combat, creating configurations where magnetic field lines of opposite polarity are forced into impossible proximity. When magnetic field lines of opposite polarity get compressed together with this kind of intensity, they do not peacefully coexist. They annihilate each other through a process called magnetic reconnection. And when that annihilation occurs, the energy that had been stored in those twisted magnetic configurations gets released in a fraction of a second, producing a solar flare. A solar flare is a burst of electromagnetic radiation so powerful that it can cross the vast gulf of interplanetary space and ionize Earth's upper atmosphere in just 8 minutes, traveling at the speed of light itself. But solar flares, as dramatic as they are, represent only half of the danger equation. Here is where the situation becomes truly unsettling. On December 1st, the sun demonstrated exactly what scientists feared it might do. An X1 9-class solar flare erupted, not from the primary complex AR4294 itself, but from a neighboring region called AR4299 that had just rotated back into view. This was a region Earth-based observers had seen before, back in November when it triggered stunning auroras visible across much of the northern hemisphere. Now it had returned for a second passage across the Earth-facing disk, and it announced its return with one of the most powerful flares recorded all year. The explosion ionized the atmosphere over Australia and Southeast Asia, causing radio blackouts that affected aviation and maritime communications for approximately 30 minutes. Satellites in orbit detected the sudden surge of X-rays and extreme ultraviolet radiation. Ground-based instruments confirmed the disruption. And yet, as dramatic as this event was, it served merely as an opening act for what might follow. Solar flares represent only half of the story. When those magnetic field lines snap and violently reconnect, they do more than emit radiation across the electromagnetic spectrum. They can also accelerate and hurl enormous quantities of physical matter into space. We are talking about billions of tons of charged particles, protons, and electrons being launched outward at velocities that can exceed 7 million kilometers per hour. These eruptions are called coronal mass ejections, or CMEs, and they represent the true harbingers of geomagnetic chaos. A solar flare reaches Earth in 8 minutes because electromagnetic radiation travels at light speed. A coronal mass ejection, being composed of actual matter, takes considerably longer to arrive, usually between 1 and 3 days depending on its initial velocity and the solar wind conditions it encounters along the way. And when that colossal wall of charged particles slams into Earth's protective magnetic field, it creates something called a geomagnetic storm. The severity of such storms depends on multiple factors: the speed of the incoming CME, its mass, its magnetic orientation relative to Earth's field, and the state of our magnetosphere when impact occurs. On December 6th, the sun struck again with renewed ferocity. AR4299 produced an M8 1-class flare, just barely shy of crossing the threshold into X-class territory. But this time, the geometric alignment was fundamentally different and far more threatening. This time, the explosion launched what solar physicists call a full halo CME, meaning the plasma ejection is heading directly toward Earth rather than off at some oblique angle into interplanetary space. The velocity measurements streaming back from spacecraft monitoring the event are staggering. The leading edge of this coronal mass ejection is traveling at 1,143 kilometers per second. That translates to more than 2.5 million miles per hour, an almost incomprehensible speed for something composed of matter rather than pure energy. NOAA has issued a G3 strong geomagnetic storm watch for December 9th. As these words are being recorded, that storm is either imminent or has already begun interacting with Earth's magnetosphere, compressing our planet's protective magnetic bubble and funneling charged particles down toward the polar regions, where they will collide with atmospheric gases and create the shimmering curtains of light we call auroras. Let that reality sink in for a moment. We are not discussing theoretical scenarios or academic possibilities. We are not speculating about what might happen someday in some distant future. This is happening right now, in real time, as you listen to these words. The CME is in transit through the void between Sun and Earth. The sunspot complex from which it originated remains magnetically active, still facing our planet, still building stress in its tortured magnetic field lines, still capable of producing an even larger event. What fascinates and terrifies solar researchers in equal measure is the direct comparison being drawn between AR4294 and the sunspot configuration that triggered the legendary Carrington Event of 1859. Richard Carrington was a British astronomer of considerable dedication and methodical precision. On September 1st, 1859, he happened to be observing the sun through his private telescope at his observatory near Redhill in Surrey when he witnessed something no human being had ever documented before in the entire history of astronomy. A brilliant flash of white light erupted across the surface of a large sunspot group he had been sketching. The light intensified dramatically over the course of approximately 5 minutes, then gradually faded back to the normal solar brightness. Carrington had no conceptual framework for understanding what he had just witnessed. The very concept of a solar flare did not yet exist in scientific literature. The connection between solar phenomena and terrestrial effects was purely speculative. He rushed to find another person who could serve as a witness, but by the time he returned with someone else, the phenomenon was already diminishing. Still, he carefully recorded every detail he could remember: the exact time, the precise location on the solar disk, the evolution of the bright patches, the duration of the event. 17 hours and 40 minutes later, the sky caught fire. Auroras erupted across the entire planet, visible not just in the Arctic and Antarctic regions where such displays are common, but in Cuba, Hawaii, Colombia, and as far south as Santiago, Chile. In the Rocky Mountains of the American West, gold miners woke in the middle of the night, absolutely convinced it was dawn based on the brightness of the sky, and began preparing breakfast. In the northeastern United States, people reported reading newspapers outdoors by the light of the aurora alone, with no need for lanterns or candles. But beneath the celestial beauty lurked technological destruction. Telegraph systems, representing the most advanced communication technology of the Victorian era, went catastrophically haywire. Operators across North America and Europe reported receiving severe electric shocks when they touched their equipment. Telegraph machines sparked and smoked even with their batteries disconnected. In several documented locations, the paper tape used to record incoming messages caught fire spontaneously. The electromagnetic disturbance was so profoundly intense that it induced electrical currents in every conductor the geomagnetic storm touched. Some operators discovered they could send messages between cities using only the electricity being generated by the aurora itself, with no batteries connected to their systems at all. The storm was literally powering the telegraph network. Now examine the sunspot currently facing Earth with this historical context in mind. When researchers at spaceweather.com carefully superimposed Richard Carrington's original 1859 sketch over modern high-resolution imagery of AR4294, the resemblance was immediate and deeply alarming. The current sunspot complex covers approximately 90% of the area that the Carrington sunspot occupied. It displays the same multi-core structure, the same magnetic complexity, the same distribution of dark umbral centers surrounded by lighter penumbral regions, the same apparent potential for catastrophic energy release. The primary difference between 1859 and today is not in the sunspot characteristics themselves. The difference is in what humanity has at stake. In 1859, the global telegraph network consisted of perhaps 100,000 miles of copper wire. Today, we depend on approximately 200,000 miles of high-voltage transmission lines in North America alone, thousands of satellites providing essential services, billions of internet-connected devices, and a tightly interconnected global economy that would collapse within hours of losing electrical power on a continental scale. The question facing us is no longer whether a Carrington-class event will happen again. The laws of solar physics guarantee that it will. The only question is when. And as solar physicists examine the data streaming continuously from NASA's Solar Dynamics Observatory, from NOAA's constellation of space weather satellites, from amateur astronomers around the world photographing the sun through specialized hydrogen alpha filters, many are quietly acknowledging that the answer might be sooner than anyone wants to admit publicly. But sheer size alone does not determine whether a sunspot will erupt with civilization-threatening force. The magnetic field configuration matters enormously. The rate at which new magnetic flux emerges from below the solar surface carries tremendous significance. The shear forces between regions of opposite magnetic polarity factor critically into eruption probability, and perhaps most frustratingly, random chance plays a role that we cannot eliminate through better instruments or more sophisticated models. We have observed giant sunspot complexes rotate peacefully across the face of the sun without producing a single significant flare. We have also witnessed tiny, seemingly insignificant active regions explode with X-class fury that caught forecasters completely off guard. The sun does not follow our predictions or respect our statistical models. It follows the fundamental laws of physics, operating on timescales and spatial scales that our instruments cannot yet measure with perfect precision. What we can measure with reasonable accuracy is probability. And right now, the probability assessments streaming from NOAA's Space Weather Prediction Center are sobering for anyone paying close attention. They have been issuing daily forecasts that place the chance of M-class flares at approximately 70% and X-class flares at 15 to 20% for the period, while AR4294 remains on the Earth-facing hemisphere of the Sun. Those percentages might sound relatively modest until you fully grasp what they mean in practical terms. We are talking about the potential for multiple major solar eruptions over a period of approximately 2 weeks. Each day represents another roll of the cosmic dice. Each flare could potentially be the trigger for something far worse than what we experienced on December 1st or December 6th. And here's the detail that truly keeps solar physicists glued to their monitoring instruments with nervous anticipation building in their chests. The massive sunspot complex has been remarkably, almost ominously quiet considering its enormous size and dangerous magnetic configuration. For 3 consecutive days, mathematical models calculated a 30 to 70% probability of X-class flares erupting from this region. Yet not a single M-class event occurred during that entire window. The region simply sat there, absorbing magnetic energy from below, twisting its field lines tighter and tighter with each passing hour, coiling like a spring under steadily increasing tension, storing potential energy with no release mechanism yet triggered. When a sunspot of this magnitude maintains quiet for this extended period, it signifies one of 2 possible futures. Either the region is gradually stabilizing and will eventually rotate harmlessly off the western limb of the sun without producing a major event, dispersing its magnetic complexity back into the solar interior as it crosses to the far side. Or it is methodically storing energy for an explosion that will dwarf anything we have witnessed in recent years, building toward a release so powerful that all the quiet days will seem like the calm before an unprecedented storm. There exists no reliable method to determine which outcome awaits us. And that fundamental uncertainty, that irreducible unpredictability, is what makes the current situation so critical to monitor with unblinking vigilance. If this documentary were being watched during the daylight hours, you could step outside with properly filtered equipment and see this sunspot complex with your own eyes. It is large enough to be visible without magnification, a dark blemish on the face of our star that shouldn't exist according to the comfortable myths we tell ourselves about solar stability. Somewhere far beneath the surface you can observe, approximately 200,000 kilometers down in the sun's convective zone, magnetic field lines are rising like serpents, twisting around each other, building the active regions of tomorrow. Some of those future sunspots will be small and inconsequential, appearing and fading within days. Others will be giants that command the attention of every solar physicist on Earth. And eventually, inevitably, one of them will erupt at the precise moment when it is pointed directly at our planet. when Earth happens to be in exactly the wrong place, at exactly the wrong time. When that moment arrives, we will discover whether our infrastructure can withstand the assault, whether our civilization is resilient or fragile, whether the preparations we have made or failed to make will prove adequate. Before we delve deeper into the current threat, we must understand that humanity has already experienced a preview of what solar violence can do to modern technology. The warning came on March 13th, 1989, and it arrived in a Canadian province that had committed no error, whose citizens were simply living their ordinary lives on what seemed like an unremarkable Monday night in late winter. The solar storm that struck Earth on that date originated from active region 5395, an impressive sprawling complex that produced more than a dozen M-class and X-class flares between March 6th and March 13th. Each eruption launched coronal mass ejections into space, creating a kind of celestial traffic jam of plasma clouds racing toward our planet. At 2:44 inches the morning on March 13th, geomagnetically induced currents found their way into Quebec's power grid. Within 92 seconds, it was over. The entire Hydro-Quebec system collapsed catastrophically. 21,000 megawatts of generating capacity went instantly dark. 6 million people found themselves without electricity in the middle of a cold March night. Traffic lights died. Elevators stopped between floors. Hospitals switched frantically to backup generators. The Montreal Metro ceased operation during what should have been the morning rush hour. Dorval Airport closed. Schools and businesses could not open because there was no power to heat buildings or illuminate classrooms. For 9 hours, Canada's second-largest province remained in complete darkness, while engineers worked desperately to restore service. Think about what that means. 92 seconds from initial disturbance to total grid failure, 1.5 minutes from normal operation to catastrophe affecting millions of people. The March 1989 storm was not even a Carrington-level event. Estimates suggest it was roughly one-third as intense as the 1859 superstorm, yet it was sufficient to black out an entire province for 9 hours, damage expensive transformers, disrupt satellites, and demonstrate conclusively that modern infrastructure was vulnerable to space weather in ways few had previously appreciated. Hydro-Quebec learned from that traumatic experience, investing approximately $2 billion in upgrades designed to prevent recurrence. But here is the uncomfortable question that lingers. What happens during a genuine Carrington-class event? What happens during a storm 3 times more powerful than what knocked out Quebec? What happens if it lasts not hours but days? The National Academy of Sciences commissioned a comprehensive study in 2008 that examined the potential impact of a Carrington-level event on contemporary infrastructure. The conclusions were genuinely sobering. The U.S. population at risk of extended power outage was estimated between 20 and 40 million people. The duration of those outages could range from 16 days to potentially 1 or 2 years, depending entirely on the extent of transformer damage and our capacity to manufacture replacements. The economic cost was projected to approach $2 trillion. These are not the alarmist projections of fringe theorists. They represent the consensus estimates of engineers, physicists, and economists who have studied the problem with rigorous methodology. There exists a witness to solar events that occurred long before any human civilization kept written records. A silent chronicler that has been documenting cosmic catastrophes for thousands of years, preserving evidence in its very cellular structure, waiting patiently for someone to learn how to read its testimony. That witness is the tree. In 2012, doctoral student Fusa Miyake at Nagoya University in Japan made a discovery that would fundamentally reshape our understanding of the sun's destructive potential. While studying the annual growth rings of a 1,900-year-old Japanese cedar, measuring the concentration of radioactive carbon 14 inches each layer, Miyake found something extraordinary in the ring corresponding to the years 774 and 775 of the Common Era. The carbon-14 concentration had spiked by 12%, roughly 20 times greater than the ordinary fluctuations caused by cosmic ray variations. Something had bathed the entire Earth in an enormous pulse of radiation over 1,000 years ago. Something far more powerful than anything recorded in human history, powerful enough to leave an indelible signature in the wood of trees around the world. Miyake's discovery was independently confirmed by research teams on multiple continents. The same spike appeared in tree ring samples from Germany, Russia, the United States, Finland, and New Zealand. Whatever had caused this event was truly global in scope, affecting every corner of the planet simultaneously. Since Miyake's initial breakthrough, researchers have identified at least 6 confirmed Miyake events in the tree ring record over the past 10,000 years. They occurred in 7,176 BCE, 5,410 BCE, 5,259 BCE, 660 BCE, 774 CE, and 993 CE. Each one represents a moment when Earth was bombarded by radiation far exceeding anything humanity has experienced in modern times. The existence of these events raises profoundly troubling questions. If the sun is genuinely capable of producing storms 10 or 20 times more powerful than the Carrington event, what would such a storm do to our technological civilization? We have estimated that a Carrington-level event could cause $2 trillion in damage and leave tens of millions without power for months. Scale that devastation up by a factor of 10 or 20, and the numbers become almost incomprehensible. 6 times in the past 10,000 years, the sun has produced storms powerful enough to leave permanent signatures in wood and ice around the world. That averages to roughly once every 1,500 to 1,700 years. We are currently living in a gap between events, a gap that has lasted more than 1,000 years since the 993 CE event. Statistically speaking, we are overdue. On July 23, 2012, the sun unleashed a monster that could have altered the course of human history. A coronal mass ejection of extraordinary power blasted away from the solar surface, accelerating to speeds exceeding 3,000 kilometers per second, carrying enough raw energy to rival the Carrington event itself. It was precisely the kind of solar storm that space weather scientists had been warning about for decades. The kind that could devastate power grids, disable satellite constellations, and send modern civilization reeling backward into a pre-electrical age. It missed Earth by approximately 9 days. 9 days in celestial terms represents the rotational difference that carried the eruption site away from the Earth-facing direction rather than toward us. If the active region that produced this massive CME had erupted roughly 1 week earlier, when it was pointed at our planet rather than harmlessly into interplanetary space, the consequences would have been catastrophic beyond easy description. We would not be speculating theoretically about what might happen during a Carrington-level event. We would be living through the multi-year recovery process, struggling to rebuild damaged infrastructure while facing cascading failures across every system that depends on electricity. Daniel Baker, director of the Laboratory for Atmospheric and Space Physics at the University of Colorado, published a detailed analysis of the 2012 near miss that reached stark, unambiguous conclusions. He estimated the storm would have caused extensive damage to satellites, potentially disabling a large fraction of GPS, communications, and weather monitoring constellations. The geomagnetically induced currents would have stressed power grids across multiple continents simultaneously, likely causing widespread transformer failures and blackouts lasting months. We dodged this bullet purely by chance. The sun does not aim its eruptions. It does not care whether Earth happens to be in the path of its violence. Active regions rotate across the solar disk, according to the sun's 27-day rotation period, erupting when internal magnetic stresses reach critical thresholds. The direction of those eruptions depends entirely on where the region happens to be pointing at the moment physics triggers the release. In the vast loneliness of the Martian surface, NASA's Perseverance rover continues its patient exploration of Jezero crater. While primarily tasked with searching for signs of ancient microbial life and collecting rock samples for eventual return to Earth, Perseverance also carries instruments that monitor the space environment around it, tracking radiation levels and solar activity from a vantage point tens of millions of miles from our home planet. Approximately 1 week before the Sunspot complex AR4294 rotated into Earth's view, Perseverance detected it from Mars. This seemingly minor technical detail actually illuminates something profound about our current ability to monitor solar threats and our future potential to do much better. The sun rotates on its axis approximately once every 27 days as observed from Earth. A sunspot that emerges on the far side of the sun, completely invisible from our planet, will eventually rotate into view over the eastern limb. During the days or weeks when that active region is pointed away from Earth, We are essentially blind to its development, unable to track its magnetic evolution, or receive any warning that a potentially dangerous structure is building on the hidden solar surface. But Mars, depending on its orbital position relative to Earth and the Sun, can sometimes observe portions of the solar disk that remain hidden from our view. When the geometry is favorable, spacecraft on or around Mars can provide advanced warning of dangerous active regions before they rotate into our line of sight. If we had spacecraft strategically stationed at multiple points around the Sun, observing it continuously from different angles, we could maintain complete surveillance of the entire solar surface without any blind spots. Active regions that currently surprise us after rotating onto the Earth-facing disk could be tracked from their earliest emergence deep below the solar surface. We could monitor their magnetic evolution in real time, assess their flare potential with greater accuracy, and issue warnings days or even weeks before they swing into dangerous, geo-effective positions. This concept, sometimes called a solar ring fence or solar sentinels, has been proposed multiple times by space agencies and researchers. The idea is scientifically elegant, but technologically and financially challenging to implement. Yet the Perseverance observation of AR4294 gave us a tantalizing preview of what systematic early warning could accomplish. As this documentary reaches you, the Sunspot complex that has commanded global scientific attention continues its slow but inexorable rotation across the Earth-facing hemisphere of the Sun. AR4294, along with its magnetically intertwined companions AR4296 and AR4298, remains one of the most visually impressive and scientifically significant solar features observed in the past decade. Its dark cores, each one large enough to swallow Earth whole, continue churning with barely contained magnetic energy. Its beta-gamma-delta classification has not changed or diminished. The potential for a major eruption has not decreased with the passage of time. And yet, paradoxically, for the past several days, the region has been remarkably, almost eerily quiet. This represents the paradox that haunts space weather forecasters and makes their profession so maddeningly difficult. The largest, most magnetically complex sunspots do not always and automatically produce the largest flares. Sometimes they sit peacefully for days or even weeks, building internal stress without release before rotating off the western limb and disappearing from view without ever unleashing their potential. Other times they explode repeatedly, hurling energy and plasma into space with each successive eruption, like a machine gun firing cosmic bullets. There exists no reliable method to predict which behavior pattern a given active region will exhibit. The physics of magnetic reconnection involves instabilities that develop on timescales too fast and at spatial scales too small for our instruments to track in real time with perfect accuracy. What we can state with confidence is that the threat discussed throughout this documentary is not hypothetical speculation or academic exercise. The Carrington Event happened as incontrovertible historical fact. The Quebec blackout happened within living memory. The 2012 near-miss happened and was documented extensively. Miyake Events have left their permanent signatures in trees and ice cores around the world, providing physical evidence of storms far exceeding anything in recorded human history. The Sun is demonstrably capable of producing events that would fundamentally alter the functioning of modern civilization, and we have done remarkably, inexcusably little to prepare for that inevitable possibility. Now, before we continue deeper into this exploration, I want to take a moment to ask something of you. If you're finding this journey through space weather science valuable, if you appreciate these deep dives into the cosmic forces that shape our world, please consider subscribing to Broken Zach. It helps this content reach more people who share your curiosity about the universe. Your support makes these documentaries possible and encourages us to keep exploring the boundaries of human knowledge. The CME launched by the M8, one flare on December 6th, has likely arrived at Earth by the time you're watching this. NOAA issued a G3 strong geomagnetic storm watch, indicating that significant auroral activity was expected and some infrastructure impacts were possible. This particular event almost certainly was not catastrophic in scope. It probably produced beautiful displays of northern lights for fortunate observers at high latitudes. It may have caused minor fluctuations in power grid operations and brief disruptions to high-frequency radio communications. Satellite operators monitored their systems closely and implemented protective measures as needed. Life continued. Civilization did not collapse. The light stayed on, but each such event serves as a reminder a warning we would be foolish to ignore. A reminder that we orbit a star capable of tremendous violence. A reminder that the infrastructure undergirding modern life was built without serious consideration of space weather hazards. A reminder that our continued safety depends on a combination of physics we cannot control and preparations we have largely failed to make despite decades of warnings from experts. The Sunspot complex will continue its rotation toward the western limb over the coming days and weeks. It may erupt spectacularly before disappearing from view, or it may slip quietly around to the far side of the sun, potentially building energy for a future display when it rotates back into Earth's line of sight approximately 27 days later. If it does erupt while still facing Earth, we will have approximately 8 minutes of warning for the radiation effects as electromagnetic energy crosses the void at light speed. We will have hours to days of warning for any associated coronal mass ejection, depending on its velocity and the accuracy of our models predicting its arrival time. That timeline is marginally sufficient for operational responses, temporarily shutting down vulnerable satellites, reducing power flows through the most susceptible sections of electrical grids, alerting authorities to prepare emergency response systems. But it remains woefully insufficient for the kind of fundamental preparations that would make a genuine difference in protecting civilization from catastrophic harm. The broader lesson of this particular moment in time is that we exist in a narrow historical window of technological vulnerability. 200 years ago, a Carrington-class event would have been primarily a spectacular light show with minimal lasting consequences. The Auroras would have dazzled observers across the globe. Telegraph wires would have sparked and smoked and occasionally caught fire. But the basic functioning of society would have continued essentially uninterrupted because human civilization did not yet depend fundamentally on electrical technology for survival. 200 years from now, if we prove sufficiently thoughtful and proactive about infrastructure development, we might have power grids thoroughly hardened against geomagnetic storms through strategic deployment of blocking devices and redundant systems. We might maintain satellite constellations designed with substantial redundancy and rapid replacement capability. We might operate sophisticated early warning systems providing days or weeks of notice before major events arrive, giving us time to implement comprehensive protective measures. The vulnerability we currently face represents a consequence of our particular moment in technological history. We are advanced enough to depend utterly on fragile electrical and electronic systems, but not yet advanced enough to adequately protect those systems from known natural threats. The question confronting our generation is whether we will use the precious time we have been given to close that dangerous gap. Every year without a major solar event represents an opportunity to invest in resilience, to harden critical infrastructure systematically, to develop the monitoring capabilities that would provide maximum warning of incoming threats. Every year without a major event is also an invitation to dangerous complacency, an excuse to assume that because nothing catastrophic happened yesterday, nothing catastrophic will happen tomorrow. We know with scientific certainty that the sun is capable of producing extreme events. We know our infrastructure remains vulnerable. We know the economic and human costs of a Carrington-level storm would be staggering beyond easy comprehension. What we genuinely do not know is when the next such storm will occur with Earth in its crosshairs. It could be decades away, arriving long after everyone currently concerned about this issue has retired or passed away. It could happen next week, next month, next year. The only completely honest answer is that we cannot predict it with any useful precision using our current understanding of solar physics. What we can do, what we must do if we value the civilization we have built, is prepare systematically and seriously. We can invest in transformer protection technologies that are already proven and cost-effective. We can develop strategic reserves of critical components that cannot be manufactured quickly. We can expand our solar monitoring network to provide early warning of threats developing on the far side of the sun where we currently cannot observe them. We can conduct the fundamental research needed to better understand and predict extreme space weather events with greater accuracy. We can take this threat as seriously as we take other natural hazards like earthquakes, hurricanes, and pandemics. Most importantly, we can stop relegating space weather to the category of exotic risks that we prefer to ignore because confronting them requires difficult decisions and substantial investments. The sleeping giant on the face of the sun may wake explosively at any moment, or it may slumber peacefully until it rotates out of our view. Either way, it will eventually return. The sun rotates once every 27 days with clockwork regularity, bringing active regions back into Earth's line of sight on a predictable schedule. And even if AR4294 fades into obscurity, dispersing its magnetic complexity back into the solar interior, other active regions will inevitably emerge to take its place. Solar Cycle 25 is not yet finished. Solar Cycle 26 will follow in approximately 5 years. The sun will continue its 11-year rhythm of activity and relative calm for as long as the hydrogen fuel in its core continues burning, which is to say for the next 5 billion years, give or take a few hundred million. We are temporary visitors in this ancient solar system, brief flickerings of consciousness on a small rocky planet orbiting an utterly average star in an unremarkable spiral arm of an ordinary galaxy. Our civilization, for all its astonishing complexity and technological sophistication, has existed for merely the blink of a cosmic eye, a few thousand years out of the sun's 10 billion-year lifetime. The sun was here long before the first human beings looked up at the sky in wonder. It will remain long after our species has either transcended to something beyond our current imagination or ceased to exist entirely. Its immense thermonuclear processes operate on timescales that dwarf all of human history. Its eruptions release energies that dwarf anything our most powerful technology can produce. Its raw power is beyond human control or meaningful influence. And yet, here we are, watching intently, measuring carefully, trying desperately to understand, trying frantically to predict, trying hopefully to protect ourselves from forces that do not know we exist and would not care about our fate if they did. The monitors will continue tracking AR4294 and its companion regions until they disappear over the western limb of the sun. The forecasters at NOAA and space weather centers around the world will continue issuing their carefully calibrated probabilistic assessments. The satellite operators and power grid managers will continue their vigilant watch, implementing protective protocols when necessary. And somewhere far below the visible surface of the sun, in the churning convective zone where plasma rises and falls in endless circulation, magnetic flux tubes are rising toward the photosphere, building the dangerous active regions of tomorrow. Some of those future regions will be small and inconsequential, appearing briefly before fading away without producing significant activity. Others will be giants comparable to or perhaps exceeding the monster currently facing Earth. Eventually, inevitably, with mathematical certainty, one of them will erupt at precisely the moment when it is pointed directly at our fragile planet. When that destined moment arrives, we will learn how well we have prepared. We will discover whether our infrastructure can withstand the electromagnetic assault. We will find out whether our civilization is fundamentally resilient or critically fragile. We will see whether the investments we made or tragically failed to make will prove adequate to preserve the technological foundation of modern life. Until then, we watch the sun with instruments of exquisite sensitivity. We wait with a mixture of scientific curiosity and reasonable concern. We hope fervently that when the sleeping giant finally wakes and unleashes its full fury in Earth's direction, we will prove ready to face the storm. The sun will rise tomorrow as it always has for billions of years before human beings existed, and will continue to do for billions of years after we are gone. Its light will warm our faces with familiar comfort. Its energy will power our world through photosynthesis and renewable technologies. And somewhere beneath that seemingly placid golden surface, the forces that could instantly transform our civilization continue their slow, patient, inexorable accumulation of magnetic energy. The universe does not pause for human convenience. The cosmos does not care about our technological dependence or our comfortable assumptions about stability. Nature follows its own rhythms according to physical laws that existed before consciousness arose and will persist after it fades. All we can do is watch, learn, prepare, and hope that wisdom prevails over complacency before the next great storm arrives. Thank you for joining me on this journey through the science, history, and implications of solar storms. I hope you found this exploration both illuminating and thought-provoking. Space weather represents one of the most underappreciated natural hazards facing modern civilization, and increased public awareness is essential for motivating the preparations we need. If you enjoyed this documentary and want to see more content exploring the wonders and dangers of the cosmos, please remember to like this video and subscribe to Broken Zach. Your support makes these in-depth explorations possible and helps spread scientific knowledge to audiences around the world. I'm curious about your perspective. Have you ever witnessed Aurora Borealis or Aurora Australis with your own eyes? Have you experienced a power outage that made you think about infrastructure fragility? Share your thoughts and experiences in the comments below. The community that gathers around these videos is as valuable as the content itself. If you found this exploration of solar threats fascinating, I have another documentary that I think you'll absolutely love. It explores a different aspect of cosmic phenomena that poses equally profound questions about our place in the universe and our technological vulnerability. Check it out next. It's a great one that builds beautifully on the themes we've explored here today. Until next time, keep looking up at the stars with wonder, but also with the wisdom to understand that the universe, for all its beauty, remains fundamentally indifferent to human concerns. Our survival depends not on cosmic benevolence, but on our own preparation, ingenuity, and willingness to take scientific warnings seriously. We'll see you in the next video, where we'll continue exploring the magnificent and sometimes terrifying realities of the universe we call home.